Welcome to this lecture on building an e-commerce project from scratch. In this session, we're going to walk through the entire process, from creating a new project and installing the right tools, all the way through planning your project properly using use cases and understanding the flow of your system. This is the kind of foundational thinking that separates developers who just write code from developers who build real, well-structured applications. Let's get into it. So the instructor starts by creating a brand new project specifically for this e-commerce application. The project is named Front-End E-commerce, referencing the date Falcon 13, which gives it a clear identity. Now, this is actually around the 5th project created throughout this series, and that repetition is intentional. By the time you've created 5 projects, the process of setting one up should feel completely natural and automatic. All the earlier projects should have made the workflow crystal clear. And if there are any errors along the way, the approach is simple. Look at the errors, address them, and move on. The tool chosen for this project is Filament. Now, if you haven't used Filament before, it's essentially a rapid application development toolkit built on top of Laravel. It gives you a beautiful admin panel, form builders, and table components without having to build everything from scratch. The decision to use Filament here makes a lot of sense for an e-commerce project because you're going to need an admin dashboard, somewhere to manage products, orders, and shops. So before writing a single line of project-specific code, the very first step is to install Filament. The installation process is straightforward. You go to the Filament PHP website, navigate to the Get Started section, and then head into the installation page. From there, you copy the very first command listed, which is the composer require command, and paste it into your terminal. Then you just let it run. And here's a really practical piece of advice from the instructor. While that installation is running in the background, don't just sit there waiting. Use that time productively to start planning your project. That's exactly what we're going to do next. Before diving into the new project, it's worth understanding where we are in the learning journey. The previous projects in the series covered 2 major areas. First, a news portal project that introduced the fundamentals, things like basic CRUD operations and routing. Second, API development, where RESTful endpoints were built and tested. The instructor points out that those 2 projects were enough to get a solid foundation, but they were basic. They didn't push into more advanced territory. This e-commerce project is different. It's where things get more sophisticated and where features need to be planned and built with real-world complexity in mind. This is one of the most important principles the instructor emphasizes, and it applies to every project you'll ever build, not just this one. Before you write a single line of code, you need to understand the project. And before you design the database, you need to understand the project. The instructor specifically mentions using tools like draw.io to design your database schema visually before touching the keyboard. Why does this matter so much? Because if you don't plan, your database ends up being a mess of tables that don't relate properly, your features don't fit together cleanly, and you spend more time fixing things than building them. Planning is not wasted time. It is development time. Now we get to what the instructor calls the single most important thing to do before starting any project, building a use case. So what exactly is a use case? A use case is essentially a description of the flow of your application. It answers the question, who are the people interacting with the system, what do they do, and what does the system do in response? Think of it like a story. You're telling the story of how your application works from the perspective of each type of user. The instructor is very clear that this is not optional. Every project you create, you should build a use case first. It's the map you follow when you start coding. For this e-commerce project, the instructor identifies 3 main actors, 3 types of people who will interact with the system. First, there's the client or customer. This is any visitor who comes to the website to browse and potentially buy products. Second, there's the shop owner, called the dokandar in the original discussion, which simply means shopkeeper. This is a business that wants to list their products on the platform. And third, there's the admin, the person who manages the entire platform behind the scenes. Understanding these 3 actors is the foundation of the entire use case. Every single feature you build will ultimately serve one of these 3 people. Let's walk through the use case flow for the shop owner, because this is where the instructor spends the most time explaining. Imagine a business, a shop, that wants to get their products listed on our e-commerce website. Here's what happens step by step. First, the shop owner visits the website. The website at this point is essentially a clean, empty front end. Then, the shop owner finds the registration section and fills out a form. This form is their request to have their shop listed on the platform. The instructor draws a comparison here to CodeAtom, a learning platform where courses are displayed. In the same way that courses are shown on that platform, the shop's products will be displayed on our e-commerce site. So the shop owner submits the form, and that triggers the next part of the flow. Once the shop owner submits the registration form, the system doesn't just sit there waiting for the admin to randomly open their dashboard. That would be completely impractical. Instead, the system automatically sends an email notification to the admin. This email tells the admin, hey, someone has submitted a shop registration request. The instructor is very specific about this. The admin gets an email so they can act on it promptly without having to constantly monitor the dashboard. This is a real-world pattern used in almost every platform that involves approvals. After receiving the email, the admin logs into the dashboard, reviews the registration details, and then either approves or rejects the shop. This is the admin side of the use case flow, and it's a critical part of how the system works. The instructor makes a really important point here about why use cases matter so much, especially for a project of this complexity. When you skip the use case step, you end up discovering missing features in the middle of development. You realize halfway through that you forgot to plan for email notifications or that your database doesn't have the right tables to support a feature you need. That means rewriting code, adding tables, and losing time. But when you build a use case first, you see the entire flow before you write a single line of code. You know exactly what tables you need, what relationships exist between them, and what features are required. For a simple project, this saves hours. For a complex e-commerce platform with multiple actors and flows, it is absolutely essential. So let's bring everything together into one clear picture. The e-commerce platform has three types of actors: the client who browses and buys, the shop owner who registers and lists products, and the admin who manages and approves everything. The platform itself sits in the middle, connecting all three. Clients see product listings, shop owners go through a registration flow and manage their shop data. The admin gets email alerts and uses a dashboard to approve or reject shops. This is the use case, the map of the system. With this map in hand, the next logical step is to design the database. What tables do we need? What columns? What relationships? And once the database is designed, coding begins, with Filament installed and ready to power the admin side of things. Continuing from the overall system flow, let's now zoom into the admin dashboard, the control center of this entire e-commerce platform. Here's how it works. A shopkeeper visits the website and fills out a request form. The moment that form is submitted, an email notification lands in the admin's inbox. The admin then logs into the dashboard, reviews all incoming requests, and decides what to do next. The admin contacts the shopkeeper manually. This is a human-to-human negotiation step, and they agree on a deal, such as a yearly flat charge or a percentage cut from every order. Once the deal is finalized, the admin performs a critical action inside the dashboard. They change the shopkeeper's status to active. This single action triggers an automatic email to the shopkeeper containing their login credentials, specifically their username and a system-generated password. This is an important design decision. When the shopkeeper first submits the request form, they do not set a password. They are not registering themselves. They are sending a request. The admin registers them internally. So the password field stays null until the admin activates the account and fills it in, then sends it via email. Now, let's think about the database design for the admin. The admin table is actually very simple. Since the admin dashboard is built using Filament, a Laravel admin panel package, it uses a default authentication system that expects exactly 3 fields: name, email, and password. That's it. The admin doesn't need extra columns like contact number or address. Keep it minimal. The admin's only job is to log in, review requests, and manage the platform. The shopkeeper, or DOCON table, is more interesting. It needs name, email, and password, just like any login system, because Filament's dashboard requires these 3 fields by default. But here's the twist. The password is set to nullable. Why? Because when the shopkeeper submits their request form, they are not registering. They're just sending a request. They don't enter a password at that point. The password will be set later by the admin when they activate the account. We also store a contact number so the admin can reach out, and a message field so the shopkeeper can describe their request. Finally, there's a status field that defaults to pending and gets changed to active by the admin after the deal is done. This is a subtle but very important design point. In a normal registration flow, the user themselves creates their account and sets their own password. But in this system, the shopkeeper is only submitting a request. They're not creating an account. The admin is the one who internally creates and activates the account. So asking the shopkeeper for a password during the request form would be misleading and wrong. That's why the password column is nullable. When the admin activates the account, they generate a password, store it in the database, and email it to the shopkeeper. This is a deliberate, thoughtful design decision. Now let's look at the product table. A product has a name, a slug for URL-friendly identification, and a description, which will be a long text field. Then comes something new, the images column. Instead of storing just one image, this system stores multiple images in a single column as a JSON array. This is a great learning opportunity. A single database column can hold a collection of values if we store it as a JSON array. The bracket symbol in the diagram represents this array format. Next is price, and then discount, which defaults to 0 rather than null. Why 0 instead of null? Because when we calculate discounts later in code, it's much easier to check if discount is greater than 0 than to check if discount exists and is not null. Finally, there's a token ID foreign key that links each product back to the shopkeeper who owns it. Let's take a moment to understand the multiple images concept, because this is something new. Up until now, you've probably stored one value per column. For example, one image file name per row. But what if a product has 3 or 4 photos? You could create separate columns like image 1, image 2, image 3, but that's messy and inflexible. The better approach is to store all image paths as a JSON array in a single column. So instead of one string, the column holds something like square bracket, image1.jpg, image2.jpg, image3.jpg, close bracket. Laravel and Filament handle this natively, making it easy to save and retrieve multiple images from one column. Here's another design decision worth understanding. Why does the discount column default to 0 instead of being nullable? The difference between null and 0 is important. Null means the data simply doesn't exist. There's no value at all. 0 means the data exists, but its value is 0. For a discount field, if we use null, then every time we write code to calculate a discounted price, we have to first check whether discount is not null and then check whether it's greater than 0. That's 2 conditions. But if we default to 0, we only need 1 condition. If discount is greater than 0, apply it. Cleaner code, fewer bugs. This is the kind of practical thinking that separates good database design from average design. The user table is straightforward. Users on this platform log in using Google Authentication, so they don't manually enter a password. However, Laravel's default user table includes a password column, and we're keeping it as is for now rather than removing it. The 3 standard fields, name, email, and password, are sufficient. After logging in, the user can browse products, add items to their cart, and place orders. The user table itself doesn't need much complexity. The interesting logic happens in the cart and order tables. When a user adds a product to their cart, we need a cart table to store that information. Let's think through what data belongs here. First, which product was added, so we need a product ID foreign key. Second, who added it, so we need a user ID foreign key. Third, which shopkeeper's product is this, a Dukan ID foreign key. Now, technically, we could derive the Dukan ID from the product itself, but storing it directly in the cart makes future queries easier and faster. Finally, we store the quantity, how many units the user wants, and the amount, which is the calculated total for that cart item based on quantity and price. All 3 ID fields are foreign keys linking back to their respective tables. Now we reach one of the most important database design concepts in this project, why orders are split into 2 separate tables. Think about it. When you place an order on any e-commerce site, you might buy a helmet, a pair of shoes, and a bag all in one order. If we stored the product ID directly inside the orders table, we could only link one product per order. That's a fundamental limitation. The solution is to split the order into 2 parts. The first table, orders, stores the overall order details: who placed it, which shop it's from, the total amount, the order status, like pending or delivered, and the payment status. The second table, order items, stores each individual product line item within that order. This is a classic one-to-many relationship in database design. Let's look at the orders table in detail. It stores the high-level information about an order. The user ID tells us who placed the order. The Dukan ID tells us which shopkeeper's store the order came from. The status field tracks where the order is in its life cycle. It starts as pending, then moves to delivering, and finally to completed. The payment status is separate. It starts as pending and then either becomes paid or canceled, depending on whether the payment went through. Finally, total amount stores the full cost of everything in the order. Notice that both status fields default to pending because the moment an order is created, nothing has been confirmed yet. The order items table is where each individual product in an order gets its own row. For every item in the cart that becomes part of an order, we create one record here. The order ID is a foreign key that links this item back to its parent order in the orders table. This is the connection between the 2 tables. The product ID tells us exactly which product was ordered. The quantity tells us how many units, and the amount stores the calculated cost for that specific line item. For example, if a helmet costs 250 rupees and the user ordered 2, the amount would be 500. Multiple order item rows can share the same order ID, which is exactly how one order can contain many products. Here's the complete picture of our database schema. We have 7 tables in total. The admin's table is simple, just name, email, and password for the admin login. The tokens table holds shopkeeper data, including a nullable password and a status field. The products table stores product information with a JSON array for multiple images and a foreign key back to the shopkeeper. The users table handles customer accounts. The carts table links users, products, and shopkeepers together with quantity and amount. And then orders are split across two tables: orders for the overall order metadata and order items for each individual product line. Every foreign key relationship you see here was derived directly from the use case flow we mapped out earlier. This is exactly why building that flow diagram first is so valuable. Let's talk about payment integration with Culti, Nepal's popular digital wallet. There are two possible approaches. Option 1, all payments go to the admin's Culti account. The admin collects all the money and at the end of the month manually pays each shopkeeper their share. This is simpler because only one Culti account, the admin's, is involved. Option 2, payments go directly to each shopkeeper's Culti account at the time of purchase. This sounds cleaner, but there's a major problem. For a normal person to receive payments via Culti, they need a merchant account. And setting up a merchant account costs around 25,000 rupees per year. If you have 10 shopkeepers, that's 250,000 rupees just in merchant account fees, which is completely impractical. So for this project, we go with option 1, payments to the admin. The most practical real-world approach for a small platform like this is actually a hybrid. The user pays via Culti by scanning a QR code, then attaches a screenshot of the payment confirmation when placing the order. The admin then manually verifies that the payment was received and confirms the order. This avoids all the complexity of merchant accounts and automated payment splitting. For this project, we implement Culti integration for learning purposes, specifically to understand how payment gateways work, and all payments are routed to the admin's account. The manual confirmation approach is genuinely the best option for a platform at this stage. It's worth being clear about the scope of this project. The goal is to touch every major feature of a real e-commerce platform, not to build a production-ready system with every edge case handled. We cover the admin dashboard, shopkeeper registration and approval, product entry with multiple images, user login with Google, cart functionality, order management with the two-table design, Culti payment integration, and email notifications. That's a lot. But things like inventory management, reviews and ratings, advanced search, and delivery tracking are left as future extensions. The instructor is intentionally keeping the scope manageable so that you can finish it and understand the full flow. Once you reach a certain level of confidence, you can add those features yourself. Before we move on, let's appreciate why the use case flow diagram is so critical. Everything we've designed in the database, every table, every column, every foreign key, was derived directly from that flow. The nullable password came from understanding that shopkeepers submit requests, not registrations. The status field came from the admin activation step. The two-table order design came from realizing one order can have multiple products. The JSON images array came from wanting multiple photos per product. This is the power of mapping your use case first. It forces you to think through every scenario before writing a single line of code. The instructor emphasizes this strongly. Build the flow, make it clear, document it properly, and the database design almost writes itself. Let's talk about why the order ID field exists in the order items table. When you have an order, you need to know which specific items belong to that order. Without the order ID stored in the order items table, there would be no way to link an item back to its parent order. So the order ID acts as a foreign key. It creates that relationship between an order and all the items inside it. This is a fundamental concept in relational database design. You use foreign keys to express ownership and belonging between tables. Reviews were intentionally left out of the initial database design. They can be added later as an extension. But when you do add them, the structure's straightforward. A review has a rating, which is an integer. Think of it as a star count. It has a message or comment field, which is a string. It needs a product ID to know which product is being reviewed, and it should also have a user ID to track which user wrote the review. That last point is important. Without the user ID, you wouldn't know who submitted the review. There's an important philosophy being shared here about how to use AI tools in development. AI is great for building things, generating code, scaffolding, speeding up repetitive tasks. But when it comes to debugging, you really need to do that yourself. The reason is simple. To debug effectively, you have to understand the code. If you hand debugging off to AI without understanding what's happening, you'll fall behind. The recommendation here is to always do at least one manual code review yourself before relying on AI to fix problems. AI is a tool to help you build faster, not a replacement for understanding. When building out your database, the order in which you create your models and migrations matters a lot. You can't create a product without first having a shop because the product table contains a shop ID foreign key. If the shop doesn't exist yet, there's nothing to reference. So the correct build order starts with admin, which has no dependencies, then shop, then product, which depends on shop, then cart, which depends on product and user, then order items, which depends on order, and finally reviews. This is the dependency chain, and following it prevents errors during migration. The admin table is kept intentionally simple. You need a name, an email, a password, and a remember token. The remember token is what allows the remember me functionality on login. It persists the session. The email verified at field that Laravel includes by default is removed here because it's not needed for the admin panel. Admins are managed internally, so email verification isn't a concern. The shop table has a few more fields than the admin table. It has name, email, and password, but the password is marked as null. There's a contact number, a message field for any notes, and a remember token. The most interesting field here is status. Since a shop has to be approved by an admin before it can operate, the status field uses an enum type with exactly 3 possible values: pending, approved, and rejected. The default is pending because every new shop starts in a waiting state. Using enum here is appropriate because the possible values are fixed and known in advance. The product table has 7 important design decisions. The description field uses long text because product descriptions can be quite long. Price and discount are both stored as double, a floating point type, because they involve decimal values. The discount defaults to 0, meaning no discount unless specified. The images field is stored as JSON in the database, but in the Laravel model, it will be cast to an array so you can work with it naturally in PHP. Finally, shop ID is a foreign key pointing to the shops table with cascade on delete, meaning if a shop is deleted, all its products are automatically deleted too. This is a subtle but important point. When you declare a column as JSON in a Laravel migration, the data is actually stored in the database as a long text, just a big string of JSON. But when you specify the JSON type, you're signaling that this field holds structured array or object data. To make working with it easier in PHP, you add a cast in the model, telling Laravel to automatically convert that JSON string into a PHP array when you read it, and back to JSON when you save it. So images, which is a list of multiple file paths, gets stored as JSON, but behaves like an array in your application code. The cart table acts as a junction between users, products, and shops. It has 3 foreign keys: product ID, user ID, and shop ID. The quantity field is an integer. You can't have 2.5 items in a cart. The amount field is a double because prices involve decimal values. Each row in the cart table represents one product that a user has added to their cart from a specific shop. The order table has 2 status fields, and the reasoning behind each is different. The order status, which tracks where the order is in the fulfillment process, uses an enum with values like pending, processing, and delivered or completed. These are fixed known states. But the payment status is stored as a plain string. Why? Because the payment is handled through Kelty, a payment gateway, and Kelty returns its own status codes: paid, canceled, failed, and potentially others. Since we don't know all the possible values Kelty might return, we can't use an enum. A string field is flexible enough to store whatever Kelty sends back. The default is set to pending. The order items table is the detail line of each order. It stores which product was ordered, how many were ordered, quantity is integer, and the price at the time of the order, amount as double. Critically, it has an order ID foreign key, which means the orders table must exist before this migration runs. If the migration files are out of order, you can rename them. Laravel runs migrations in file name order, so adjusting the timestamp prefix in the file name controls the sequence. The review table needs both a product ID and a user ID. The product ID tells you which product is being reviewed. The user ID tells you who wrote the review. This is a common oversight. Sometimes only the product ID gets added, and then you lose track of which user submitted which review. The rating is stored as an integer, and the comment is a string. The schema should be fully finalized before you start coding, because changing foreign key relationships after the fact causes significant rework. Now let's talk about Eloquent relationships, how you define the connections between models in Laravel. There are 2 simple rules to follow. Rule 1, if your table contains someone else's foreign key, you use belongs to. For example, the cart table has a product ID, so the cart model belongs to the product model. Rule 2, if your own primary key appears in someone else's table, you use has many. For example, the shop's ID appears in the products table, so the shop model has many products. And there's one more naming convention to remember. Belongs to uses a singular model name, while has many uses a plural method name. Let's walk through the shop model's relationships. The shop's own ID appears in 3 other tables: the products table, the carts table, and the orders table. All of them have a shop ID column. That means the shop model has three has-many relationships: has many products, has many carts, and has many orders. The shop model itself doesn't contain any foreign keys from other tables, so it has no belongs to relationships. It's a parent in all its relationships. The cart model is a good example of a table that only has belongs to relationships. Looking at the cart table, it contains three foreign keys: product ID, user ID, and shop ID. Each of those means a belongs to relationship. Cart belongs to product, cart belongs to user, and cart belongs to shop. Now, does the cart's own ID appear anywhere else? No. No other table references the cart ID. So the cart model has no has-many relationships at all. It's purely a child in all its relationships. The order model has relationships in both directions. On the belongs to side, the order table contains a user ID and a shop ID, so the order belongs to user and belongs to shop. On the has many side, the order's own ID appears in the order items table as order ID, so the order has many order items. When naming the has many method, you can use either items or order items. The plural form is what matters. This bidirectional relationship is very common in e-commerce schemas. The order item model has two belongs to relationships. It contains an order ID, so it belongs to order. It also contains a product ID, so it belongs to product. The order item's own ID doesn't appear in any other table, so there are no has-many relationships here. Order items are leaf nodes in the relationship tree. They reference other tables, but nothing references them. The product model has relationships in both directions. On the belongs to side, the product table contains a shop ID, so product belongs to shop. On the has many side, the product's own ID appears in three other tables: the carts table, the order items table, and the reviews table. So the product model has many carts, many order items, and many reviews. Product is a central table in this schema. It's referenced by many other tables. The user model has no belongs to relationships because the user table doesn't contain foreign keys from other tables, but the user's own ID appears in three places: the carts table, the orders table, and the reviews table. So the user model has many carts, many orders, and many reviews. The user model, like the shop model, is a parent in all its relationships. Other tables reference it, not the other way around. The review model, like order item, is a leaf node. It only has belongs to relationships. It contains a product ID, so it belongs to product. It contains a user ID, so it belongs to user. Nothing else in the schema references the review's ID, so there are no has-many relationships on the review model. This completes the full relationship map for the schema. When your model has fields that store data in a non-standard format, you need to tell Laravel how to interpret them using the casts property. The most common cases are arrays, like the images field, and dates. For images, you declare it as array in the casts, and Laravel will automatically convert the JSON string from the database into a PHP array when you read it, and back to JSON when you save it. Normal types like strings, integers, and doubles don't need any special casting. Laravel handles those automatically. Only JSON and date fields typically need this extra configuration. By default, Laravel protects your models from mass assignment, meaning you can't just pass an array of data directly into a model without specifying which fields are allowed. This is controlled by the fillable property on each model. But during development, adding fillable to every single model is tedious. A shortcut is to call model unguard in the app service provider's boot method. This disables mass assignment protection globally. It's a convenient approach while building, but in a production application, you'd want to go back and add proper fillable arrays to each model for security. This application has three distinct types of users, each with their own login system. Admins log in to manage the platform through the admin panel, shops log in to manage their products and orders, regular users log in to browse, add to cart, and place orders. Each of these corresponds to a separate database table: admins, shops, and users. And in Laravel, each will have its own authentication guard configured. This multi-guard setup is a common pattern for applications that serve multiple types of authenticated actors. So the instructor wraps up the login system setup by making a very important point. Any model in your Laravel application that needs a login system must follow a specific structure. The most critical part is that the model must extend the authenticatable class. This is what tells Laravel that this particular model, whether it's an admin, a shop, or a regular user, is capable of being authenticated. Without this, the login system simply won't work for that model. The instructor walks through the specific traits and properties that need to be present in any authenticatable model. First, the model must extend authenticatable. That's non-negotiable. Then you have the hasFactory trait for generating test data. The hidden array is used to protect sensitive fields like passwords from being exposed in API responses. The fillable array controls mass assignment. And finally, the casts array handles things like automatically hashing passwords. The instructor points out that the easiest way to get all of this right is to simply copy the structure from the default Laravel user model, since it already has all of these set up correctly. The instructor demonstrates a practical shortcut here. Instead of writing all the authentication boilerplate from scratch, you simply open the default Laravel user model and copy the relevant pieces: the extends authenticatable declaration, the hidden array, and the casts array. Then you paste them into your new model. One interesting thing the instructor discovers during this process is that the import for authenticatable is actually aliased from the user class. It reads use illuminate foundation auth user as authenticatable. That's why when you try to import it fresh, it might not auto-suggest correctly, because internally the class is named user, not authenticatable. The instructor applies this same authentication structure to two different models, the admin model and the shop model, which is referred to as the DOCON model in this project. Both models get the same treatment. They extend authenticatable, include the hidden array to protect passwords, and include the cast array for password hashing. This is a great example of how Laravel's authentication system is flexible. It's not just for the default user model. Any model in your application can be made authenticatable by following this same pattern. At the end of the session, the instructor makes it a point to commit all the work to Git and push it to a public repository. This is good practice. Saving your progress after each working session ensures you never lose your work and gives students a reference point to check their own code against. The instructor also notes the session date as Falcon 13 in the Nopali calendar and updates the mentor and student resources with the new link so no one misses the session recording. During the live session, a student named Avinash shares their screen and encounters errors, null images, and null titles showing up on the page. The instructor walks through the debugging process carefully. The first instinct might be to look for a code bug, but the instructor quickly identifies that the real issue is actually a data entry problem. The articles in the database were added without selecting a category, so when the Vue tries to loop through articles belonging to each category, it finds nothing, and that causes the null values to appear. The instructor's solution is clean and elegant. Instead of always trying to render the article block for every category, you wrap it in a conditional check. The fix is to use an @if statement that checks whether the count of articles belonging to that category is greater than 0. If the category has no articles, the block is simply skipped. No null values, no errors. The instructor explains the logic clearly. Some categories might legitimately have no articles, and your Vue code needs to handle that gracefully, rather than crashing or showing empty data. This debugging moment leads to a broader best practice that every developer should internalize. You should never assume that a relationship will always have data. When you're building views that display related models, like articles belonging to a category, always add a guard condition before you try to render anything. The instructor's approach using count greater than 0 works perfectly. You can also use Laravel's built-in isNotEmpty method on Eloquent collections, which reads even more naturally. The key lesson here is to always test your views with both full data and empty data, because in real-world applications, empty states are completely normal. Let's bring together everything that was covered in this session. The main focus was setting up a proper login system for multiple models in Laravel, specifically the admin and shop models. The key takeaway is that any model needing authentication must extend authenticatable and include the hidden and casts arrays. The instructor also walked through a real live debugging scenario where null values in the view turned out to be a data entry issue, not a code bug, and the fix was a simple conditional check before rendering. The instructor wraps up by mentioning that starting from the next session, the project will follow a use case-driven development approach, which means building features based on specific real-world scenarios. To close out this entire series of sessions, here are the 3 most important things to walk away with. First, Laravel's authentication system is not limited to just the user model. Any model can be made authenticatable by extending the right class and including the right properties. Second, don't reinvent the wheel. The default user model is your template, and copying from it saves time and prevents mistakes. And third, always write defensive Vue code. Real-world data is messy and incomplete, and your application needs to handle empty states gracefully. These principles, reusability, correctness, and resilience, are what separate a beginner's code from production-ready code.